Good afternoon, everyone. Welcome to the latest topic, Stat 543. This is logistic regression. Now, logistic regression is very similar to linear regression, except now our response variable y is either 0 or 1. Now, there are several applications, but we're not limited to these. Part reliability. Did the part work or did it fail? Survival analysis. Did the organism live or did it die? Genetics. Is the gene turned on or is it turned off? And my favorite, sports. Did the team win or did the team lose? Now, we've got a continuous numeric predictor here. However, when we recall our two-sample t-test, X was a predictor, but it could be a group control or a treatment, while Y was a response variable. It was continuous. But with logistic regression, our X variable is continuous, but now our response is going to be either 0 or 1, as you can see in the picture. Now, a scatter plot here that we would use in linear regression is not going to be very useful. As you recall, with linear regression, we had residuals, and the larger they got, the less useful the line was, the less strength that we had. However, with logistic regression, no matter what line we put in, we're going to obtain very large residuals. So instead of finding our linear relationship between X and Y, now we want to look at the relationship between X and the probability that Y is going to be 1, i.e., what's the probability Y is going to be a success given we're at some X? Well, with logistic regression, we've got the natural log of the probability of success over 1 minus the probability of success. And we're going to set that equal to our beta 0 plus beta 1 times xi. Recall, beta 0 in linear regression was the intercept, beta 1 was the slope. Well, this is going to be our logistic transformation. We don't know that the probability at I is going to equal yi, and in fact, the probability at I is not going to equal yi. Instead, we're going to use this logistic regression package that's available in R. Now, in order to determine what the probability at I is, we're going to have to look at a little bit of math. Now recall, the natural log of pi over 1 minus pi, we set equal to beta 0 plus beta 1 xi. Well, if we exponentiate both sides, we can see we get e to the natural log of pi over 1 minus pi is going to be e to the beta 0 plus beta 1 xi. Now, what we want to solve for is pi. So, this gives us pi over 1 minus pi equals e to the beta 0 plus beta 1 xi. If we multiply both sides by 1 minus pi, we get pi by itself. It equals 1 minus pi times e to the beta 0 plus beta 1 xi. However, we're going to have to expand this a little bit. And what we come up with is that pi equals e to the beta 0 plus beta 1 xi minus pi times e to the beta 0 plus beta 1 xi. We can add pi times e to the beta 0 plus beta 1 xi to both sides. And what we now get is pi plus pi times e to the beta 0 plus beta 1 xi equals e to the beta 0 plus beta 1 xi. Factoring out our pi, we get pi times 1 plus e to the beta 0 plus beta 1 xi equals e to the beta 0 plus beta 1 xi. And if we now divide and get pi by itself, we see pi equals e to the beta 0 plus beta 1 xi over 1 plus e to the beta 0 plus beta 1 xi. Now, when we're looking at how beta 1 is going to be affecting our logistic regression equation, notice that in this slide, beta 1 is less than 0. And so we see we've got this downward curve. However, in this slide, beta 1 is going to be greater than 0. And so we get this upward trend. Now, what we need to be able to do is make sure that we can interpret the results. But in order to interpret the results, we've got to make sure that our algorithm converges. So when might we not have convergence? Well, in a case like this, we don't have convergence. The problem we have here is that on one side of this line, we have all failures. On the other side, we have all successes. Now, what this gives us is a vertical line. The problem we have is that with a vertical line, we have an undefined slope. And with an undefined slope, we could have multiple, infinite number of possible lines that could possibly be the best fit. This means that we've got many possible curves. Therefore, there is no unique solution. Now, when we're using R, what we'll find is that it may give us a line of best fit, but this is an approximation. It's not the line of best fit. With separation, there is no line of best fit. Now, the easiest way to determine this when we look at R, we're going to see that R is either going to tell us that the algorithm didn't converge, or it may possibly give us number of iterations is 25, in which case that's our magic number. If we hit 25 iterations, that means we were unable to converge. So what are we actually trying to do with logistic regression? Well, one thing we'd like to find is our inflection point of our curve. When does our curve go from positive to negative, or from negative to positive? Once we find that inflection point, we found the place where we are more likely to be 0 or 1, and this is where we switch from being more likely to less likely, or less likely to more likely. So how can we interpret beta 1? What does beta 1 actually mean? Well, we have no idea. Beta 1 in this case has no meaning. Okay, we'd like to interpret this. We'd like to interpret this natural log of pi over 1 minus pi that equals beta 0 plus beta 1 xi, but there's a problem here. We're actually looking at an odds ratio. Pi over 1 minus pi, this is an odds ratio. So in trying to interpret beta 1 using this, what we would be saying is for each 1 unit in x, we expect a beta 1 unit increase in the log odds success. However, this makes absolutely no sense. So we're never going to interpret beta 1 in logistic regression. So then that leads us to question, what good is beta 1? Well, recall, we're exponentiating beta 1. So we can interpret this. Now, what this means is that for each 1 unit increase in x, we expect an e to the beta 1 times increase in the likelihood of success. This does make sense. It's telling us e to the beta 1 refers to how many times more likely y is to be 1. So if we look at beta 1 and how we could interpret it, suppose beta 1 is less than 0. Well, this would imply that e to the beta 1 is less than 1. So e to the beta 1 is e to the beta 1 times less likely. If beta 1 equals 0, this implies e to the beta 1 equals 1, and this means that we're equally likely. And if beta 1 is greater than 0, then e to the beta 1 is obviously greater than 1, so we are e to the beta 1 times more likely. So how do we create confidence intervals with logistic regression? Well, recall, beta 1 plus or minus z star with our particular confidence times the standard error of beta 1 hat. Well, remember, our confidence interval is simply a point estimate plus or minus the margin of error. So the question we may have, why are we using z star here instead of t like we did with linear regression? Well, remember, we're looking at a proportion of successes. And anytime we're dealing with proportion, we're using the z's. Therefore, if we expand this out, we get beta 1 hat minus z star times the standard error of beta 1 hat, and beta 1 hat plus z star times the standard error of beta 1 hat. Now, beta 1 hat and the standard error of beta 1 hat are both going to be found in the R output, and we can then just convert these by exponentiating both. What about our hypothesis test? Well, recall, we could test for no relationship, in which case our alternative hypothesis is not equal. We could test for positive relationship, in which case our alternative hypothesis is greater. We could test for negative relationship, in which case our alternative hypothesis is less than 0. Our test statistic here is then going to be z equals beta 1 hat minus beta 1 sub 0 over the standard error of beta 1 hat, where again beta 1 and the standard beta 1 hat and the standard error for beta 1 hat are both found in the R output. And this is going to be normally distributed with a mean of 0, 1. Other uses we can have for logistic regression involve what's called classification. Now, we've got equal options if we suppose that pi is 0.5. In other words, where are we equally likely to be a success or failure? If we plug in 0.5 for our pi, then we get natural log of 0.5 over 1 minus 0.5. Well, that equals natural log of 1, which is 0. We can then solve for x. So what we have is 0 equals beta 0 plus beta 1 xi, and this is our point in which we switch from likely to unlikely. Now, in classification, what we're trying to do is we know that here we are at 0.5. Why is 0.5? We're equally likely or unlikely. What we're doing is back solving to find out what our x value would be. In this particular case, what we found was that x was 13.88.